Standard geometry allows us to map the physical world using angles and perpendicular lines. David Hilbert pioneered the mathematical framework that extends these same geometric rules to abstract, infinite-dimensional spaces. This diagram shows two vectors in a standard coordinate system. Using normed and Banach spaces, we can calculate the length of these vectors and the distance between them, which allows us to define limits and convergence. Knowing the distance between 2 points is insufficient for determining their orientation. As these vectors pivot, the distance between them changes, but a standard norm provides no way to tell if they are parallel, intersecting, or exactly perpendicular. By generalizing the concept of a dot product, we can define the vertex and lock these vectors into a precise 90-degree angle. An inner product provides the structural rules needed to define orientation, allowing us to navigate abstract spaces with geometric rigor. In 3D space, vector A casts a vertical shadow onto vector B. The inner product measures that shadow's magnitude, establishing dependency. When we rotate A perfectly upright, the shadow disappears. They are now orthogonal. Their inner product is exactly 0. To function in any abstract space, an inner product must satisfy 4 axioms: linearity, scalar multiplication, conjugate symmetry, and positive definiteness. In complex vector spaces, conjugate symmetry dictates that the product of x and y must equal the complex conjugate of y and x. When a vector is paired with itself, this axiom forces the result to equal its own conjugate. Since only real numbers possess this property, the calculation ensures the vector's length never results in an imaginary number. Because the inner product of a vector with itself is guaranteed to be a real positive value, we can take its square root. This formula defines the norm, or the exact length, of the vector. While every inner product automatically generates a norm, the inverse is not always true. This requirement makes inner product spaces a stricter, more geometrically consistent category of vector spaces. We can apply this logic to a wide spectrum of spaces. In Euclidean space, we compute the inner product through a finite sum. In function spaces, we use an integral to measure the overlap between 2 continuous curves. In every case, the inner product is limited by the Schwarz inequality. Mathematically, the product of 2 vectors can never exceed the product of their individual lengths. This provides a geometric bound, ensuring calculated angles behave exactly like traditional trigonometry. To determine if a generic normed space supports an inner product, we use the parallelogram equality. Here, we use vectors x and y to form the sides of a parallelogram, with the diagonals defined by their sum and difference. If the sum of the squares of the diagonals equals the sum of the squares of all 4 sides, the space possesses an underlying inner product. This geometric symmetry is the definitive proof that the space supports angles and orthogonality. This identity serves as a mathematical tool for uncovering the deep geometric structure hidden within abstract vector spaces. A Hilbert space is an inner product space that also possesses completeness. In these spaces, if a sequence of vectors gets progressively closer together, we can be certain it is moving toward a specific limit. Completeness ensures that this limit actually exists within the space. Without it, a sequence could converge toward a mathematical whole, a point that the space simply does not contain. This stability is vital for modeling physical systems. Quantum mechanics uses Hilbert spaces to define energy states as orthogonal vectors, and ensures that as we analyze infinite limits, our physical observables converge to real, measurable values. This sequence shows the evolution of mathematical spaces. We start with a basic vector space, add a metric for distance, a norm for length, an inner product for angles, and finally completeness to secure our limits. A Hilbert space unites algebra, geometry, and analysis. This structure allows us to treat infinite-dimensional problems with geometric intuition, ensuring that our mathematical models remain consistent when describing complex physical systems.